everybody to our materials seminar this week. And it's my great pleasure to introduce Dr. Zeier to you, whom I have known for a long time. I was actually your TA. I was his TA in when we were young, when we both studied chemistry in Mainz in Germany. So we've known each other for quite some time. So Dr. Zeier, he received his PhD from Mainz and in Germany, as I said, and then went to the States for a postdoc and did his postdoctoral work at the University of Southern California with Brent Milo, and then switched to Northwestern, right? I don't have a cheat sheet, so I'm just gonna do it out of the top of my head, and worked with Jeff Snyder, whom I met, by the way, a week ago when I visited Northwestern, and we had a nice lunch together in person, which was really fun. And then Wolfgang went back to Germany to start his basically more or less than independent career in Gießen in Germany with Professor Jürgen Janek. And then now he is a professor at the University of Münster in Germany, and he has more or less a long history of working with solid-state batteries, looking into solid-state materials, a lot of structure properties, relationships, and we're going to hear about this today in his talk, and we're very excited that you're here, Wolfgang, and very happy that you agreed to be here on a Friday night, German time, so it's just shortly past 8 p.m. And for all of people in the audience, please mute yourself. And if you have questions, please post them in the chat or indicate that you have a question. And then after Dr. Zeier's talk, we will go through all of the questions subsequently. So Wolfgang, the virtual floor is all yours.
Thank you, Christina, for the kind introduction. And when you just mentioned that you were a TA, do you remember what it was? I think it was PChem, and it was actually ion conduction in liquids measuring transference numbers. And here I am, and I'm going to be talking about ion transport. So I guess you sort of put that pathway down to some extent.
Nice to think about it that way.
Right. I just realized that this is what this was.
Yeah.
No, really, I appreciate the opportunity to talk a bit about the work that we've been doing and trying to get a better understanding of ion transport in solid ionic conductors, and I'll talk a bit about solid-state batteries as well. And so where would I put my group? Just to give you an overview, I think we're sort of physical inorganic materials chemists, and I think the group is sort of put on 4 pillars that predominantly work on ion conduction of solids. So typical approaches of better understanding ion diffusion, and this is something I'll talk about today. We work a bit on lattice dynamics of ion conductors and even thermal transport of ionics. And some part of my group focuses on solid-state batteries. And so these 2 pillars, I'm going to give you at least a flavor of what the group is doing. Well, there's currently, I would say, a lot of people are currently talking about solid-state batteries, sort of as the new thing in the. So I'm having an echo. Right now we have solid-state batteries as the sort of the next goal in the battery community, right? If you think about the lithium-ion battery, we all use that on a daily basis. It has a cathode, so an active material that can reversible intercalate lithium ions. We usually have some sort of graphite anode, a thin separator, and a liquid electrolyte that nicely wets and all active particles and ions can percolate really nice from cathode to anode during charge discharge. This comes up with a few challenges. I mean, you've heard information like media reports about fires, and they're not that common, but there are safety concerns. And I think we all want our cars to be able to drive for further distances than what we currently have. And the current thought is that solid-state batteries may be able to supply that by replacing this liquid electrolyte with a solid ionic conductor, and by replacing the graphite anode with, for instance, a lithium metal anode. And the challenge that now comes is that here in the liquid battery, you have a liquid electrolyte that wets all of your active particles. And in a solid state battery, now you have active components that are solids, and you have a solid ionic conductor. So you have grain-grain contacts you need to take care of, you need to be able to process these materials. You really need good interfacial contact, because if there's a lot of porosity, you're going to have a large problem. You need electrolyte stability. Like these ionic conductors, even though they're ceramics in many senses, they're not stones, so they decompose at certain potentials, and you need a high ionic conductivity. If you have a bad ionic conductivity, you have a high resistance between your electrodes, and your battery's just not going to work. And so there is this push of going solid in the battery community, and on top of that, we need to really have fast ion transport. And this is something I want to talk about today. Why is that important? Well, ideally, we'll have, and I'll say this now, and I'll probably kill that statement at the end of my talk, but right now we roughly need 1 millisiemens per centimeter of an ionic conductivity for battery operation. And if you plot literature data of conductivities for various materials classes, let's look at the argyrodites class that I'll show today. Within the same structure type, your conductivity branches over orders of magnitudes. And your activation barrier does as well, even though this is the same structure type. And so our job is sort of to figure out, we want to always figure out why that is the case and which knobs do we need to tune to push these ionic conductivities. Well, what is ionic conductivity? This is a very simple process. It's in principle an ion sitting on a lattice site that is adjacent to an empty lattice site, and the ion just needs to jump from one side to the other. By doing that, it needs to displace the lattice a little bit. That costs energy, so the whole jump is associated with a delta G. And if we have enough energy to overcome this delta G, ideally it ends up in that final state. And now, depending on the structure and how the coordination of the ions are, we get a certain energy landscape. So for instance, if we assume that this ion is just much more happy being this trifold coordinated, it'll have a lower energy than here in our square planar coordination. Meaning that even if we overcome the barrier, the lithium would sit here and it has a much higher probability to just jump backwards. This is sort of the baseline of the structural community, that we know that our crystal structure itself gives us the energy landscape of the ion, or at least that's what we mostly think of. And so if you go to textbooks, inorganic chemistry, you'll find a variety of things that are allegedly affecting ionic conductivity. That is a number of available sites. You need space to jump into. If everything is occupied, nothing will be moving. You need a certain polyhedral conductivity. So for instance, if you look at an hexagonally close packed lattice, you have a lithium sitting on a tetrahedron and it wants to jump to the adjacent tetrahedron, needs to go via this triangular site. This is well connected via a phase. And so if you think of this in terms of a chemical reaction, there's no change of the reaction coordinate. But if you think of it like this, then you change your coordination from 4 to 3 to 4. That's cleaving one bond, that's forming a new one that doesn't cost a lot of energy. But for long range transport in the structure, you would then have to jump via an octahedral site. So the coordination changes from 4 to 3 to 6. That costs a lot more energy. And then the lithium is, in this case, unhappy to sit on an octahedral site. So if we overcome the barrier, it's more likely to just jump backwards. So a lattice like this with a lot of octahedra and tetrahedra is usually not a good ion conductor. So the polyhedral connectivity matters, and in the change of the coordination environment. And one of the typical approaches, I would say, that we have in ionic conductors is let's just blow up the unit cell. Because if this displacing the lattice is what costs a lot of energy and what gives us our activation barrier, then let's just make larger unit cells, so broaden the diffusion pathways. And in most materials, this broadening of the diffusion pathways gives you a lower activation barrier. Now, so this is truly our our typical playground in ionic conductors. And there's newer thoughts that people have working on softer, more polarizable lattices. This is why currently a lot of push in the field is on working on sulfides and halides compared to oxides, for instance, or phosphates. And I'll also be mostly talking about these sulfides and halides today. So I've split the talk in three subtopics. The first two are just purely on solid ionic conduction, and two materials classes that we've been working on for a while and that we sort of fell in love with in the group, because they don't follow the typical behavior of, oh, let's just make it bigger and it's going to be better. No, there's a lot of influence of synthesis and structural disorder, and this is something that we've started to play around with, and we're trying to get a better understanding, and I'll try to bring across what we currently understand in these materials. And at the end, I'll talk a bit about ion transport in batteries, because you'll see that just making or having good ionic conductors really doesn't mean that they're good when you put them in the cell. All right, I would say in the first part, we'll talk about the so-called argyrodites, the lithium diophosphates, so Li6PS5X. And this X is a halide, so a chloride, a bromide, and iodide anion. The halide forms an FCC lattice, and you have these ortho diaphosphate PS4 3- tetrahedra pretty much sitting on the octahedral sites. And then you have a free sulfur S2- anion that's in half of the tetrahedral holes. And for a long time, we said, well, the lithium is somewhere in there. And this somewhere in there, for us, always was some sort of lithium cage that forms around the sulfur anion. And so the jumps that you can have is sort of lithium jumping from here to here, and it can jump back, and that doesn't give you much. It can jump from one of these so-called duplets to another one, and they can fast rotate around their cages, and this is what they do. But long-range ionic transport means we need to jump from one of these cages to the next one. And by doing that, it needs to bypass a halide. This halide will become important. Now, when we do a topological analysis of these lithium sites that we have here right now, projected into 2D, you see that these cages, they're actually fairly isolated. It's a long jump. It's too long for it to be happening. Yet these materials, they're some of the best ionic conductors for lithium that we have out there. Why is that the case? Well, it seems that this lithium substructure is incorrect. We actually found an additional lithium substructure that makes this cage seem a little bit more clustered. And what it really does, it connects these formerly unconnected clusters or cages to each other. So we do have a really good connectivity in there in certain compositions. Well, why certain compositions? Well, there's something that we call a site disorder in these materials. What is actually found is that depending on the halide that you use, some of the halide could be sitting on the sulfur side. This is very prominent in the chlorides. So the chloride anion has the same ionic radius as the sulfur 2- anion. So in the synthesis, they can just easily exchange. It's the same ionic radius. So some chloride anion will be sitting here, some sulfur will be sitting here. And in the chloride case, this is roughly 50 to 60%. So really statistically entirely disordered. Interestingly enough, when you go to the bromide, this disorder decreases up to 20–25%, where 20–25% of the bromide is sitting here. So bromine is just larger, a lot less fits in that cage. And as soon as iodine is in there, iodine will just sit on its lattice side. It's just too big to sit in these small cages, so to say. But when you plot measured ionic conductivities versus the site disorder, and you fit some arbitrary function over it, just to sell you that there's an optimum, it does look like there's an optimum. Well, but what we definitely know for sure is that the disorder is beneficial for ionic transport. Why is that the case? We already see that if we calculate so-called bond valence sum maps. It's pretty much a fancy word for, is there enough space for ions to jump around? And so in the structure is fully ordered, you see these heat maps where lithium is just rotating around the cages. And when you turn on this order, the cages start connecting and lithium just jumps around in the unit cell. Well, why is the disorder important? To figure this out, we looked carefully at nutrient diffraction, temperature dependent, starting from low temperatures to nail down the lithium substructure. And we tried to analyze it in a different perspective, not the typical where are the positions in principle and what are the occupancies. So we looked at first the iodide material that has 0% disorder. And here's a function, pretty much a radial distribution, so a number of lithium ions as a function of the distance from the center of the cage. And don't mind the nomenclature that we have here, but in principle, we have these two positions that I talked about earlier. Now, when you go to the bromide, you get that additional position. Mind, this is a material where we have this order, and there's more lithium further away from the center of the cage. If we go to the chloride, that's even more pronounced, and more pronounced in the sense that it's really far out from the center of the cage. And this is weird, right? When we're an iodide, it's a large unit cell. The bromide is a smaller unit cell. The chloride is the smallest unit cell. But even though we have the smallest unit cell, the distances in the unit cell, they're larger. Why is that? Well, we thought about to like, instead of looking at these radial distributions, we're now going to define a mean radius, the average radius weighted by occupancies away from the center of this cage. And if we plot this radial distribution as our mean as a function of the disorder, this our mean increases as a function of disorder. Why? Well, I think this is fairly simple. We have a rearrangement of anionic charges. So at 0% disorder, it's all S2 minus in the center of the cage, and S2 minus will be very coulombic attractive to the sulfur, to the lithium. Now we turn on the disorder. The central charge, the central anionic charge decreases. It's less negative because now there's a bromide on it. So there's less coulombic attraction, they can expand. And if we put the chloride on it, they expand even more. So let's now assume that at least as our mean is some sort of a descriptor of the homogeneity of the lithium distribution in the unit cell. Is it a good descriptor for ionic conductivity? We'll see that in a second. But first, we want to figure out why there even is any disorder. And this is some work that my student Ajay worked on, who's I saw in the audience, and he's looking for postdoc positions. And just FYI. So Ajay had this really cool idea to look at the bromide-based argyrodites and run different synthesis routines. So the typical approach of making these materials is you stick them for 2 weeks in a furnace at 550 Celsius. You just turn off the furnace, and whatever comes out, comes out. And whatever comes out is this gray dashed line on 22, 25, I guess 22% site disorder. Now I decided, okay, let's do this differently. Let's make the material, but keep it at a certain reaction temperature, or 550 reaction temperature, and just quench after a certain time frame. So he kept the material in for 1 minute and quenched, crystallizes fully already, and it has a much higher site disorder. If he runs it for 5 minutes or 30 minutes, or I guess that's 5 hours, still same high site disorder, just by quenching. If he runs the standard cooling approach, we end back up at our 22 degrees. This tells us that at higher temperatures, this order is favored. At lower temperatures, it's less favored. So the quenching sort of kinetically traps the disorder. To corroborate that idea, we cooled the furnace in a slow cool approach over 5 days. Much more we shouldn't do, I guess. And the lowest site disorder we get is sort of 13%. So slow cooling makes it order into its thermodynamic phase, that like the thermodynamic ordering that it actually wants to be in there, or at least as close as possible. And we do see that there's the direct correlation between this disorder and the conductivity. The quenched materials with the higher disorder have a higher conductivity. So if we go back to this initial plot, if you quench them, you get higher disorders, you get higher conductivities. Now we thought about, okay, let's see how much we can push this thought of synthesis matters here. So instead of quenching them after different times at 550 Celsius, we decided to quench them at different temperatures. So usually you would think nothing should happen, but a lot actually happens. And our site disorder is a direct function of our synthesis temperature. If you quench from 550, you're at 40%, and the lower your quenching temperature is, the lower you are in this order. At some point, nothing changes really, because if you quench a material from 100 Celsius, it's already in the state where it wants to be in there, because you still need thermal energy for ions to diffuse around and to swap sites. But again, I think the story here is that the quenching really traps the site disorder, and this disorder seems to be entropically favored at elevated temperatures. Now let's use this, bring this back to this R mean that I was talking about earlier, this average distribution. And here, this is another example where this R mean is a direct function of up here the site disorder, or down here the average charge on this central site. So the lower the central charge is, the further apart these cages are. And this is a much more meaningful study than looking at these chloride, bromide, and iodides, because we're now not changing the nature of the anion. Now we're just in the bromides. So the chemical composition of all these materials is the same, but we have an entirely different lithium substructure just by quenching, disordering these halides and the sulfide position. And when you take neutron diffraction data and you calculate the isosurfaces of where lithium can be found via the so-called maximum entropy method, you actually see that the cages at low disorder, they're much more constricted, and the cages at high disorder, they're much more spread out. So there's really a much better connectivity the more disorder there is. And our collaborators from Darmstadt actually looked at that in MD, and you really see that if you use a material that has no disorder, these ions just rotate fast around around the cages, but there's no jumps happening. As soon as you turn on this order, lithium moves throughout the whole unit cell, and these materials become amazingly fast ionic conductors. And so we can plot in the study of quenching from different temperatures, the ionic conductivity versus the site disorder, and it scales directly with the site disorder, or it scales directly with this R mean. So really, by tailoring synthetically this disorder, we can directly affect the ionic conductivity. And I was actually baffled by this, because oftentimes, at least in our community, we have a problem, or the issue that one group may synthesize an ionic conductor and another group can't really match these ionic conductivities. And this happens to everyone. And the reason clearly is that even small changes in the synthesis procedure, being it that you didn't map out your furnace, or that the ampule that you reacted wasn't right in the middle, but maybe 5 centimeters out, so your actual synthesis temperature is wrong, or maybe you did quench it and it's not reported, like small things that oftentimes we're not paying attention to, can actually have a tremendous influence on the ionic transport in these materials. But by using this R mean, we can actually push the ionic conductivity to much higher values, and values that are in the end actually useful in cells. All right, this was the first part of the story on anion disorder. Now I'm going to give a similar story, but on cation disorder in another class of materials where we also see that synthesis plays a large role. I would say in the last, well, I guess since 2018, there was a really great paper by Panasonic showing lithium, yttrium, lithium, erbium, chlorides, and bromides to be fast ionic conductors. They ball milled them, used them in solid-state batteries, and they ran extremely well. If you go into the literature, all these materials were made in the 90s, and they were horrible ionic conductors. So if you look at the logarithmic plot of ionic conductivity with temperature, this is the classically prepared materials back from the 90s. So in the end, you use your precursors, you stick them in an ampule, and you heat them up, and what comes out is a bad ionic conductor. If you ball mill the materials, just the precursors, no heat treatment, they're really good ionic conductors. Why? Well, let's look at the structure real quick. The structure has, in the end, an erbium position that sits on the corner of the unit cell. You can have an additional erbium 2 position sort of in the middle, like 2 positions in the cell itself, and you can have a third erbium position that sort of make these virtual chains along the Z direction. They're not going to be occupied all the same time, because if erbium 3+ is right next to an erbium 3+, that's just Coulomb-wise not gonna work. But in principle, there's these 3 positions. The lithium sits somewhere in the middle, and the somewhere in the middle is forming a honeycomb lattice of octahedra. And so you can, in principle, have a good diffusion in the AB plane, and in the Z direction, there can also be good diffusion. But this doesn't really explain why there's this difference in ionic transport. And so Roman, the student that worked on this project, so I took a sheet out of Ajit's playbook on quenching materials. So we used the ball mill sample, had them in a furnace at 550 Celsius for a minute, quench it. Conductivity decreases. He keeps them in for an hour and quenches them. Conductivity decreases, and it comes further and closer to the one that we get from classic solid state synthesis. Why? Well, we actually see that the ionic conductivity, like I said, decreases, and the activation barrier increases from the ball milled, here called as prepared, to the ampule synthesis. Well, with structural chemists, we usually try to stick everything in a beam and see what the structure comes out. The problem is, if you ball mill precursors, it's going to look like this. So this is nothing that we can actually refine in reed-filled refinement. The crystallized ones we can. 1 minute annealing, it's crystalline, that's remarkable, but not really part of this part of the story. So this is something where we can solve the structure. So we need to look at the pair distribution function of these materials. And PDF is in the end just a histogram of atom-atom distances, and this can help us. We can refine these or even look at them qualitatively, and we'll do that now. For instance, you see that here the PDF, so this atom-atom histogram trails off really fast, loses intensity. It tells us that it's pretty much an amorphous, some sort of glass-like material, whereas crystallization gives us really crystalline pair distribution functions. Let's look at them first qualitatively. Down here, the PDF of the ball mill sample, up here, all the PDFs of the crystallized sample. What we see as direct difference is that in the as prepared sample, in the ball mill sample, there's one bond distance missing that is prevalent in all of the other ones. And this corresponds directly to this erbium 1, erbium 2 distance. Whereas there's an additional distance here in the ball milled material that is not really there in the crystallized materials. And this is the erbium 1, erbium 3 distance. Qualitative is not quantitative, so we can refine these PDFs, and of the crystalline material, you can also refine the diffractograms. And what we see is that in the ball milled sample, there's an erbium 2, erbium 3 disorder that is roughly 97%. So when you ball mill the material, you actually already locally form your structure, but it's not ordered. You have erbium sitting more on this side than on this one. And the more time you give it in the furnace to relax into its thermodynamic minimum, the disorder decreases. It's still there, even in the ampule synthesized material, but it's minimal. So we have this disorder in the structure. And if you then plot your conductivity as a function of site disorder, you see that the more disorder you have, the higher your ionic conductivity. And the more disorder you have, the lower your activation barrier. So really, this disorder directly influences the ionic transport, and milling makes these materials just so much better ion conductors. Why does this really affect the ionic transport? I think right now we don't have an answer yet. What we think is happening, and this slide we need to take with a grain of salt, because here I'm pointing at anisotropic thermal displacement parameters obtained by a neutron diffraction from powder. And, the caveat here is the powder. But what we do see is that when you go from your ampule synthesized material to your ball milled material, is that the one lithium position starts pointing more upwards for an in-plane ionic conductivity. So what we're thinking is that by disordering, sort of by moving erbium down from this side to this one here, there's a little bit more repulsion on some of the lithium, and it just pushes it more in the Z direction. And so that the ampule materials, they're mostly diffusion in plane. And as soon as you have this order, you actually get three-dimensional diffusion. This is our current working hypothesis. If this is true, this is something that we'll have to figure out in the foreseeable future. All right, enough of ion transport in solid electrolytes. I hope you saw that we can understand ion transport in a variety of materials, and we can push ion transport to be competitive. And I said earlier that all you really need is 1 millisiemens per centimeter of ionic conductivity, and these materials, they have that. What I'm going to show now is that it's really not enough. It's not enough of a conductivity. And the example I'm going to use are lithium sulfur solid state batteries. So not using NCMs, or not using these intercalation type oxides, cathode active materials, but making it a bit more complicated. By a bit more complicated, meaning instead of having just an ionic conductor and a cathode active material, an oxide in there, we're now going into 3 phases where we have sulfur, we have carbon, we have our solid electrolytes. And there's a few major changes and challenges that come with this. The first one is your sulfur has really high volume changes. So if you convert sulfur to Li2S, you have an 80% volume increase. Whereas in these oxide materials is only 6%. And this is something the 6% are already a problem if your active material is breathing right next to a grain of an ionic conductor. An 80% volume increase is a problem. But even more so is that now we need transport in 3 main phases. It's no longer just 2, but now it's 3. It's carbon that we need because sulfur is an electronic insulator. It's a sulfur, our active material, and it's our solid electrolyte. And why is this a problem? Well, let's look at a charge-discharge curve, and I don't usually show a lot of those, so bear with me, of a solid-state battery, a lithium-sulfur solid-state battery in purple, directly compared to a conventional one that is in liquid electrolytes. And you see that the capacities, or the amount of charge you can put in reversibly and get back out, is very similar for both cell types, irrespective if we use a solid electrolyte or if we use a liquid electrolyte. But the overpotential between these curves, so in the end, the resistance that we have between our electrodes is much worse in the case of the solid state battery. Are the kinetics just more sluggish? I don't know. So we really need to look at what ion transport actually means if we think in terms of a composite electrode. Now there's in principle 2 ways that we can measure this. The simpler way that we use most of the time, and this is so-called DC polarization. So in the end, you polarize your setups with here an electron blocking current collector and an ionic blocking configuration, and in the end you just measure ion curves. So you use Ohm's law and you get a resistance out, and with that resistance we can calculate an ionic and electronic partial conductivity. This works in pure composites. It does not work in full cells. In full cells, what one can do is use the so-called transmission line model, where we sort of model this complicated multi-phase behavior in the cathode composite as a bunch of resistances that are ion conducting resistances, a bunch of electronic conducting resistances, and transverse impedances in between. And transmission line modeling has been used in solid-state batteries, but we weren't sure if it can be used in lithium sulfur cells because they're a bit more complicated because they're 3-phase. Now, what my postdoc back then decided to do is let's try and do this systematically and see if we get the same values that we would get if we do DC polarization. So we built sort of carefully symmetric cells where we sort of change the loading, look at the transmission line model, and extract the resistances, the ionic resistances and the electronic resistances in the cell. Ionic resistance increases with thickness of the electrode. The electronic resistance increases with the thickness of the electrode. And if you back calculate that into ionic conductivity, it actually ends up fairly well where your effective ionic conductivity would be from DC. So the DC are the polarization measurements. All of this here is impedance. So transmission line model works. Now we can use that to measure the ionic transport in these composites. This is a complicated plot, and I'll walk you through it. This is the measured ionic conductivity, our effective ionic conductivity, so the ionic conductivity that we have in the composite as a function of the volume fraction. This effective ionic conductivity is a function of the volume fraction, the tortuosity factor, so how tortuous a pathway is through a composite, and the ionic conductivity of your pretty much untouched electrolyte, so 100% solid electrolyte. The first thing that we see is actually very interesting. When you make these composites, you usually ball mill them. And here we have a fast ionic conductor, and when we apply the processing conditions that we use to making composite electrodes, the ionic conductivity drops, which is a little bit counter to the statement I said earlier that ball milling is good. So let me amend that statement. Ball milling is good if you want to make a fast ionic conductor, but if you keep ball milling it, you're going to make it worse. In any case, we can measure this effective ionic conductivity as a function of the volume fraction of our electrolyte. First, we do that with just solid electrolyte carbon composites, and then with solid electrolyte carbon sulfur composites. But this is sort of the composition or the volume fraction of solid electrolyte that we have in a composite cathode. This is the ionic conductivity up here that we wanted, or let's say we're at 1 millisiemens. This is where we started with. By putting these ionic conductors in a multi-phase composite, the ionic conductivity drops over 2 orders of magnitude. 2 orders of magnitude is way too much. For those of you that are familiar with the battery field, there's a so-called Bruggemann relationship that is used to model these like tortuous pathways in liquid cells, and this would be this behavior. So in solid electrolytes and solid-state batteries, it's actually worse. What does this mean? Well, by this drop of the conductivity, we build up a much larger resistance in our cell, because ion transport in these composites, it's no longer fast. So initially it was fast. We put a little bit of carbon in there, and from a race car, it becomes a Vespa. And the more carbon you put in there, the slower your lithium becomes, because you're just increasing your fraction of ionically insulating material, the carbon and the sulfur. But we really have sluggish ion movement in these solid-state batteries. And the take-home message here is, 1, we need much faster ionic conductors. So far, we're all using materials that are between 1 and 5 millisiemens, and 5 millisiemens per centimeter used to be a good value. But if you drop your ionic conductivity by 2 orders of magnitudes, in reality, you need 2 orders of magnitudes better ionic conductors for solid-state battery operation. And this is something that we always forget. So the materials that we currently have, they're good enough to build these batteries, and they're good enough to figure out the fundamental challenges that we have, but they're not good enough for like a real-time operation. Because when you really want to use them for something later on, you need thicker electrodes, you need a lot of active material so you can actually hold a lot of charge, and for that you need much faster ionic transport. Or another option is we sort of design the microstructure of our composite, and that might lead to less tortuous pathways. So thinking in terms of like columnar arrangements of these batteries, how viable that would be for an upscaling, surely debatable. But what we do learn from all of that is that it takes careful balancing of the effective transport, in this case, the lithium ion transport, but also your electronic transport. If your electronic conduction is too low, you have the same problem. And so, for instance, if you play with the volume fraction of your solid electrolyte and your carbon, you just by playing with that volume fraction, keeping the sulfur ratio the same, you can optimize the actual capacity, so the amount of charge that you can store in these sulfur batteries. But this is quite doable. It's just a big engineering problem, I would say. The third problem in solid-state batteries, in lithium-sulfur solid-state batteries, but in other types of solid-state batteries that use ionic conductors, especially the sulfides, is that we will have decomposition of the electrolyte. Why is this a problem? Well, decomposition, this is a schematic charge-discharge curve, voltage versus the capacity, the area underneath. So you would discharge a material, the area underneath is the energy that you get out. Now, in reality, you have a resistance between your electrodes. Oh, wrong direction. So when you charge your material, you get some sort of overpotential. When you discharge your material, you get some sort of overpotential. If you now start decomposing your material, you build a resistive interface. This gap becomes larger, which means the energy that you get out at the end is a lot less than what you put in. So you're constantly losing energy. And you might actually kill capacity because you're breaking apart your active materials as well. So decomposition is a bad thing in principle. Well, if there's a Yifei Mo, he's in Maryland in, it's now 6 years ago. He put out this really cool paper showing the potential windows of solid electrolytes that people are using. And just to walk you through this graph, anything that is at 0 means it's stable against lithium, for instance. All of the lithium binaries, they're thermodynamically stable against lithium by definition, of course. But the materials, for instance, the argyrodites that we're working with, oh my goodness, they have very narrow chemical stability windows. They shouldn't even be working in these solid-state batteries, but they do. And interestingly enough, if you run a typical CV of a solid electrolyte with planar electrodes, like most people do, these materials are stable up to 5 volts. Well, if you use an electrode that has larger surface areas, or you make a composite out of it, you already see in your CV that there's a lot happening. So they're not that stable. And what one can do is run stepwise CV, where we increase sort of the reversal potential by 0.1 volt, go back and so on. And once we start a lot of current increase and additional features showing up, we know that our electrolyte is decomposed. And we can do this oxidative. Green means it's stable. Down here in reductive regime, green means it's also stable. So the decomposition range that we're in, or the stability window, is actually a little bit larger than the thermodynamic one. So the kinetic stability in the end. But the question is, does this affect our transport? So what we did is we kept using this approach of the transmission line modeling for the impedance data of these full cells. And instead of actually running these batteries, we just kept them at specific potentials for 12 hours, went back to open circuit voltage, and then measured the impedance, just to look at how does the resistance in these cells change. The first thing that we can see is here in blue is the potential range that we see based on the CVs where it should be stable. Up here is the cumulative charge. So as soon as the charge goes up, means there's something flowing, which means we're decomposing our electrolytes. And here is the total resistance of the cell, and here's the ionic resistance of the cell. And here the red dashed lines would be the stability window based on thermodynamics, so based on Yifei Mo's calculations. In blue, this is the stability window that we get from our CVs. And you see up here in the charges that as soon as we hit that, some charge is flowing. So we're really decomposing our solid electrolyte. Usually not a good thing to decompose your electrolyte in a battery, but the resistance doesn't change up to a certain higher potential and lower potential. Here shown in green, the total resistance doesn't change, the ionic resistance doesn't change, and your effective ionic conductivity also doesn't change. That means we have some sort of stability window for an effective ion transport. We can run our electrolytes outside of their stability window, and it's not bad for the battery. Well, let's use that by changing the upper and lower cutoff voltage that we cycle our cells with. So if you cycle it entirely outside of the stability window, there's a lot happening and the cells crash really fast. But if you restrict it to this effective stability window, they run actually fairly well. And so you see that this overpotential evolution from here as an example, 5 to 50th cycle is high if you run the cell way outside of the stability. If you run it within the stability, even though there's decomposition, it doesn't affect the performance. But you still have that large overpotential in between charge and discharge. So effective ion transport, just because it doesn't get worse, doesn't mean that it's good enough for good cells. Yeah, and with that thought, I think I want to wrap up. I think the take-home message here for that is that just because we have good ionic conductors does not mean that they're good enough in the cells in the composites. And lithium sulfur solid-state batteries have a few challenges. They have these chemomechanical problems that I said, that so sulfur is expanding to lithium sulfide. I didn't talk about that really today. We have this electrolyte degradation that can be a problem depending on how we run it. But I think more so is the fact that we have these tortuous carrier pathways. And this argument is the same for any type of composite-based solid-state battery. You also see this drop of the effective ionic conductivity if you use the oxide cathode active materials. And so here there are tremendous challenges for these sulfur-based solid-state batteries. But I think in all reality, this is the highest, because that just means we need much faster ionic conductors. And if you sort of project some sort of roadmap for lithium sulfur solid-state batteries, here are projected energy densities of NCM-based, so oxide-based solid-state batteries. And this is the current state that we're at. Well, it's really not enough, but just by using a lithium metal anode, making your electrolyte the separator thinner, and putting more sulfur into the material, and all of that depends on making faster ionic transport happen. Lithium sulfur solid-state batteries might actually surpass the NCM-based ones. But that's a lot of ifs, because that really means, same for these materials, for these cells, 5 millisiemens is not enough. It needs to be north of 50, ideally 100. And that's quite a lot, to be honest. Yeah, with that, I thank you for your attention. I hope I was able to show that synthesis and preparation methods strongly and hugely influence the local structure of these ionic conductors, and that this order is actually very important in these materials. And I hope I was able to show that truly, to better understand how ions are moving, we shouldn't just look at the electrolytes. We also need to look at, for one, not just the interfaces either, but also really the transport in composites. And that there's really a strong influence of this whole idea of, well, we have composites, there's tortuous pathways, and there's a lot of engineering that we need to do. And with that, again, I thank you for your attention. I need to thank my group. It's not like I do any of this work. It's of course the team and a variety of collaborators involved from theory and the beams that we use, and of course the funding. And as a large shout out, I'm always looking for motivated postdocs and doctoral students. So if you find any of this work fun to pursue in your scientific career, just send me an email and we'll chat. Thank you. I'm sure you have questions.
Thank you, Wolfgang. I'll send an application shortly.
You don't want to come to Münster, it rains too much. Oh, I shouldn't have said that now. Huh?
Okay, well, thank you so much. That was a great talk. I know that there's already questions in the chat and we do have some time for them. So I'm just gonna take the liberty of asking the first question because I'm already talking. So I really liked the first part where you made it very clear that synthesis parameters matter, and they matter a lot for the properties, even if a material basically kind of looks the same, you know, based on the bulk structure. This is how I understood it. So that was a really, really valid and valuable point to make. And my question would be, you said quenching affects the disorder and that there's a clear correlation with the conductivity. My first question to that point would be, you measure the bulk and you look at the local structure, right? Can you basically exclude that through quenching you might have some segregations
No.
that might influence also the conductivity, and they could be amorphous or low in crystallinity and they wouldn't pop up in the bulk structural analysis?
I hate that question. No, no, we cannot rule this out for a simple reason. These sulfides, if you want to really annoy a TEM specialist, put a sulfide in their high vac TEM systems and let the electron beam nicely evaporate all of the sulfur. So we don't know if there's any segregations, if they sit on the grain boundaries and so on. The question about amorphous contents is an important one. It's heavily debated, and the honest answer is I don't know. We see that in certain materials, there's residual features in the PDF that can hint at, so if you do a differential PDF, that could hint at an amorphous background, where, for instance, we just see these PS4 signals. We often, at the beginning or a few years ago, we interpreted that as a glass phase. There's newer work that sort of suggests that is actually also additional PS4 disorder that is just not mapped out. There are certain materials that seem to have additional glass phases, and that seems to depend on the composition. So the honest answer is it's magic. We don't know. And the problem really is that even, like, for one, you can't do any electron scattering on those electron diffraction, and these are very soft materials that whatever you do with them, you wouldn't even see anything on the grains. Excellent question. I get this asked a lot, and for 5 years now, I've always said I don't know. Because I don't have a good idea. Okay, thanks. Maybe an easier question to answer. Can you do something else to increase that local disorder except for quenching? I'm just talking purely experimentally. Have you thought about that? Yes. But you're not going to tell me. I'm not going. I cannot tell you, but yes, we have. Okay, then I'm just going to leave it at that, and I will go through the other questions that we have. Let me see, where's my chat? Those are long things, so if people are still around, Ramandeep, if you don't mind, please unmute yourself and could you just ask your question? Then I'm not missing any nuances of it.
Okay, yeah. So my question is that when you're replacing ions in the structure, you're increasing the ionic conductivity. And also you're increasing the strain energy due to the size mismatch of these ions. What are the main properties that are compromised due to the increase in the strain in the structure?
Which strain are you talking about in the structure?
There is no strain in the structure. So you start with a structure, which is a primary structure, and then you replace the cations and anions, right?
Yeah, so if an answer for this chloride bromide iodide system, well, these are pure solid solutions. Like there's really no strain in the material, like at least the macroscopic strain, put it this way. Locally, there can be. strain is an important question when we talk about this whole quenching and different treatments of these materials. If you look at least if you look at these Williamson-Hall plots, it doesn't look like we're inducing any strain by quenching it. So I'm not sure if they're actually strained in the sense that having here macroscopic strain or microscopic strain, either or, in the materials that I've shown here. In a different type of ionic conductor, like the sodium Na3PS4, so a sodium thiophosphate, there seems to be straining between the ball milling and the ampule work. It's at this point, it's unclear if the straining does help or not. There's in the oxygen ion conducting field, there is enough work done that if you strain a lattice, if you open it up a little bit, especially at interfaces, you increase diffusivity. But I think in these materials, we just don't know yet.
Okay, can I ask another question?
Go ahead.
Okay, so there is some short range order, as you said, in the structure. At what point does it translate to phase separation or any kind of precipitation? Any thermodynamic studies on these? No, it
doesn't. This disorder, this is the same chemical composition of the materials.
Okay.
There's you will have phase segregation if you start putting different elements in there, but all of the stuff that I've shown here is pretty much the same chemical compositions.
And are these material by any chance entropy stabilized? If you like,
I would assume so. I would assume so. At least the ones that we quench from high temperatures like that. But this order is purely entropy based. Well, we don't know. We try to sort of calculate how much disorder we would get from entropy, and the disorder increases if we use configurational entropy, but it doesn't truly match the experimental data. So there might be something else as well. But yes, entropy is playing a large role. Absolutely.
All right. Thank you.
Of course.
Shu Hao, if you would like to ask your question, please go ahead.
Yeah, I'm here. Thank you for your very interesting and very fantastic presentation. Because the disorder structures from the first part and the second part, the cation anions, they are from like the quenching or the ball milling, the synthesis the methods. And for the quenching, we know that mostly they are not the thermodynamic stable at room temperature. For the ball milling, we are not sure. So, like for the second part, when you anneal the ball milling, the samples, their conductivity decreases. So my question is that the diffusion, or really used in the batteries, or like the many cyclings, where the diffusion or the electrochemical reactions will play a similar role like the annealing to make the disordered structures more like the ordered structures to promote this transition. And then so is the conductivity stable after many cyclings in the batteries?
So if I understand the question correctly, you're asking if the field that we would have applied, if that changes the disordering, right? If this high disorder is stable under like constantly running currents back and forth. No idea. This is an excellent question. No idea.
So
the reason why we don't really know is in these cells that we're using, we have, I would say, our cathode, and we would have to look at this problem in the cathode, is 50 microns thick. So we have roughly 8 milligrams per square centimeter of ionic conductor. And we should look at that in neutron diffraction, I would say, so we can actually figure out what happens, let's say, with chloride and sulfur, or at least with lithium. And that would mean making a lot of batteries to get a cube centimeter of volume. What we have not done yet is keeping them at a certain, like, polarized for a very long time. When we run polarization experiments, and we do that to measure partial electronic conductivities after the polarizations, the disorder has not changed. but these are measurements that are performed over a few days.
Yeah.
What happens after weeks or months, I don't know. This is an excellent question.
So is it possible to assemble these disordered materials into the batteries and let them charging, discharging cyclings for like several months and then measure their conductivity again to confirm?
Yeah, but they decompose. They decompose, right? So what we would have to do is look at the structure after all that cycling. And if you want to then actually look at that in a beam, you would have to go from an 8 milligram loading that we have per cell and make enough cells to have a cube centimeter for neutrons, which is in this case 2.3 grams per cube centimeter. So that's a hell of a lot of cells to get enough volume for neutron diffraction. So I don't know yet. I've been asked this question before. This is an excellent question, really. I think we don't know yet. Collaborators have looked at that to some extent. In their simulations, they didn't see much happening, but the truth is, in their simulations, they never saw that the anions swap places anyways. So who knows? Really good question.
Yeah, thank you for your answer.
Thank you. Going down, Danush, if you're still around, please go ahead, ask your question. Okay, I'll ask it in case they left. So thank you for the nice presentation. In the argyrodites, you showed the ionic conductivity peaks for around 50% site disorder and then decreases. Why does it decrease at a higher site disorder?
This is fairly simple. Let's assume you have 100% site disorder. Then you just swapped your anions, right? Which means then sulfur is on the other side. So at some point, initially your cage, the lithium sits around the sulfur. You put a halide in, it starts expanding, but at 100% disorder, your cage just sits here around the sulfur again. And then you have the same. So this is really a mirror image in the structure in principle. And that's why the optimum is somewhere in between. That you need to have charge homogeneity, I would say, like a nice distribution of your 1 minus and 2 minus anion that really flattens out your energy landscape, spreads out the lithium nicely. At least that's how we interpret it.
That makes sense.
In the MD, you actually see it that it's suddenly on the other side.
Mm-hmm. Next question is by Yoon. Yoon, are you still around? And I think Candice, she indicated that she's also interested in Yoon's question, but Candice had to leave due to another meeting.
I'm still here.
Okay, great. Go ahead.
Yeah, thank you very much for a great talk. I really enjoyed that talk.
Thank you.
So I'm interested in your solid state lithium sulfur battery work because I'm working on lithium sulfur battery. Especially the plot that you showed, the ionic conductivity as functional volume of solid electrolyte in the composite electrode was very interesting. So did you consider the contact resistance of the solid state solid electrolyte particles when you did this? Because I think because sulfur melting temperature is so low, so you cannot sinter a solid electrolyte particles in the composite electrode. So you might have pretty much the contact resistance in between the solid electrolyte particles, but I wonder how effective that term would be in the electrochemical behavior.
That's the beauty about the sulfides. You don't have that contact resistance. They're so mechanically soft. You just squeeze them together. And everything. This is I didn't mention that, but this is with a chloride and argyrodites. This is with a sulfide. It's just their bulk modulus is at, I don't know, 10 gigapascal or 5 gigapascal or something like that. With just a little bit of pressure, you really compress all of the grains, and there's not a lot of grain boundary resistance in there. It's not an oxide. This is why this works.
Oh, I see. That's interesting.
Yeah, but this is an excellent point. In an oxide, we would have the additional grain resistance for sure. Yeah.
Oh yeah. Okay. Thank you very much. Yeah, that answers my question.
Of course.
Thank you, Yoon. Yeah, and it's recorded. And also, I think Candice, she said, thank you for the great talk. And she wanted to contact you by email. And I do not see any further questions. So I'm asking the audience if there are any further questions. You feel free to unmute yourself and ask it.
Christina, this is
Yeah,
Krishna.
Go ahead. Yeah.
Just, I had to step away for a couple of minutes, but I assume that you didn't show too much NMR work. Have you considered carrying out orthogonal NMR work to look at lithium residence times and diffusion and correlate to the effect of disorder?
Yeah, we do that. Usually in collaboration. I didn't show any of that work here, but it does correlate.
Oh, it does correlate. Okay.
It does correlate, yeah.
Cool.
It's really the case that impedance, NMR, and theory actually tell the same story. So
yeah, that's great. I mean, that's great. I mean, yeah. I mean, just very quickly. I mean, do you see these chemistries working well for sodium?
The battery chemistries. Or,
yeah.
Yeah. No. It's. So the ionic conductors for sodium, they're much faster.
Yeah.
Like sodium is, even though it's bigger, it's just much faster in the solid state. So one would think you can actually make 40 millisiemens. So one would think if we translate that to sodium, this would be better. The problem that we have is that all these sodium materials, they're much more unstable against sodium metal. So these materials here, these lithium materials, they decompose against lithium, but they form a passivating interface. Against sodium, they form an interface that just keeps growing and runs through a whole battery.
Okay.
And on the cathode side, they're even less stable against the cathode active materials that one can find for the sodium. And we really don't know why. If you look at the literature, people have made cells with sodium, and they run okay-ish if one uses CIS2 is used, or in terms of the oxides, it's usually sodium chromite, so NaCrO2. Those cells work, but you really don't want to use chromium in these cells. And as soon as you put iron in there, and iron would be ideal because for sodium you can actually make iron, sodium iron oxide, then nothing runs anymore, and we don't know. So it might be sort of a devil's game that in the sodium materials we have the ionic conductivities that we need, but the interfaces are so bad that, at least at this point, the sodium solid state batteries are not running this well throughout the whole community, I would say. But it doesn't mean that no one's working on them. I think everyone's trying to make them work.
Cool. Thanks, Wolfgang.